The last two problems on this page, one is exponential and one's logarithmic, so we can follow the strategy that we developed. Remember, first we want to isolate the part that has the x stuck in it. So here we have an exponential expression where the x is stuck in the exponent, and so I want to isolate that, 3 to the minus x. So I do that by adding 7 to both sides, and then dividing both sides by 2, and I'll have 3 to the minus x equals 4. From there, we want to convert this into a logarithmic equation. Let's put this down. And so this is base 3 exponential expression, so it's going to be equivalent to a base 3 logarithmic expression. And I always like to write the entire equation out and then fill in the blanks. The 4 will go here, the minus x will go here. So we swap input and output. And so our solution then is we can multiply both sides by -1, and our solution is that x is negative log base 3 of 4. So that is the exact answer. Don't forget that that our change of base formula tells us that in the calculator you would enter that as the minus sign is still there, but to do the log base 3 of 4, we do log of 4 divided by log of 3. And it doesn't matter which log button you use on your calculator, as long as you do that ratio, that's equivalent to log base 3 of 4. And so that's what you would want to use. This is perfectly fine as the exact answer. In fact, that's a good exact answer. But if you're going to get the answer rounded up to 3 decimal places using a calculator, you'll need to enter it like that, since most of you don't have a log base 3 button. Letter F, remember that LOG just means log base 10. And we do that because that's what your calculator button is log base 10. So we put some of these problems on there just to make sure you know what your calculator is doing. This already is separated. The log part is already by itself on the left side, so you can say it's equivalent to the equation where the input and output are swapped. So this was the input into the logarithm, and so that's going to be the output in the exponential, and -1 was the output of the logarithm, and so -1 is the input into the exponential. Remember that the point here is to free the x up. So if you do something and your x doesn't get freed up, then that's when you know you've done it backward. So the only reason we do it is because the x is stuck in the log, and so if I ended up with an equation where the x was stuck in the exponent, then I know that I did that wrong. So anyway, so 10 to the minus 1 is just 1/10, and so this is easy to solve. I can add 3 to both sides, and I'll have 5x equals 3.1, basically 3 plus 1/10, and so x is whatever that is, 0.62, I guess. So that would be the exact answer. There's no more decimal places to that. On this page, we're working with functions both with composition and with domain and range. So don't forget that the composition notation FOG of x means f of g of x, and so we can approach this the same way we did with numerical values. First, look up what g of x is. In this case, it's just 2x minus 6. So we replace the g of x with 2x minus 6 because that's what it's equal to, and then the f function the f function takes an input and does 1 over the square root of that. So when we give f this input, we will get 1 over So in analyzing the domain here, you can do your analysis from that final answer, or you can just think about what's happening at each stage in the evaluation. As we go from this step to this step, there's no possible x that could cause a problem. G of x's domain is all real numbers, and so when you change g of x into 2x minus 6, there's no possible error that could happen. But when you go from this step to this step, the domain of f becomes relevant. And if you look at the f of x definition, we can see right away that the x's can't be negative because they're under a square root sign. But also the x can't be 0 because it's in the denominator of a fraction. So we have two different possible problems with f of x. And the net result is that the input into f, so the domain, the domain of f is positive numbers. You can't put anything in there besides positive numbers. So when we combine these two things, what we have is that the input, this 2x minus 1, that's going into f, has to be positive. So we conclude that 2x minus 6 has to be positive. And if you add 6 to both sides, that means 2x is greater than 6, and so x is greater than 3. So the domain of the composite function is x is greater than 3 as an interval. So the domain of f of g as an interval is just 3 to infinity, again with rounded brackets or rounded parens around 3 because we don't want to include 3. If you're not sure whether to include 3, don't forget that that's an easy thing to check. If you can't decide whether 3 should count or not, just try putting 3 in here, and you'll see that it gives you an error. It'll give you a division by 0 error. So, so if you're not sure, plug it in and check. So in part A here, these are the ones that we would typically do by graphing the function, graphing a few points of the function, and that's certainly a good way to do it. I would say that thinking about your intercepts first is probably a good idea, just because those are easy to do without having to visualize anything else. So the intercepts are, remember, the y-intercept happens when x is 0, so we'll have 2 minus 2 to the 0, which is 1. So 0, 1 is my y-intercept, and the x-intercept happens when the function is equal to 0, that's when the y-coordinate is equal to 0, and that happens when x is negative 1. And those are solved just like the ones on the previous page, so looks like that. So those are my intercepts. Now maybe plot f of 5 and f of minus 5. Give yourself a couple of values out further away because this is an exponential expression, and so we expect one of those to be close to the asymptote and the other one to be gigantic. So f of 5 is 2 minus 2 to the minus 5, which is 2 minus 1 over 32, which is very, very close to 2. So by the time the function gets out here to 5, the graph is still not quite to 2, but it's getting awfully close. And so that gives us the idea that the asymptote here is y equals 2. On the other hand, if I put in minus 5, I'll have 2 minus 2 to the minus 5, which is negative 30. And so that is way down here. So we have this sense that the graph is plummeting to the left and approaching the asymptote y equals 2 to the right. And so the domain of this then is minus infinity to infinity. Exponential functions don't typically have domain problems. It's the range that's always of interest to exponentials, and what we're looking for with the range is that the asymptote should be a barrier to the y values, so the asymptote should be the barrier to the range. So the range here, minus infinity, because the graph is falling down off the screen, up to 2, not including 2. We don't think it gets there. For logarithmic functions, we expect to have a vertical asymptote, and so we expect there to be some kind of domain issue. But again, let's first start with the intercept. So the y-intercept happens when x is 0, so that's log base 3 of 3, which is 1. And so this graph has a y-intercept at 0, 1, and the x-intercept happens when the y-coordinate, in other words the formula, is equal to 0. And to solve that, we could change that to exponential. So 3 to the 0 equals x plus 3. And so x plus 3 equals 1 happens when x is negative 2. So you want to check the algebra on these things. These equations are just like the problems on the previous page, and so hopefully you can see how to solve them. So now the asymptote for the logarithmic function, I'm not going to just put in some extreme values because, well, the domain of logarithmic functions is not minus infinity to infinity, so the graph's not going to exist in both directions. What we do instead to find the domain of a logarithmic function is we think about where the argument for the log, in other words, the stuff in parentheses, is positive. That's what needs to happen. You can't take the log of anything other than positive numbers, so take the stuff in the parentheses for the log and think about when that is greater than 0. And so if I subtract 3 from both sides, that tells me that x has to be greater than -3, which as an interval would be the interval -3 to infinity, not including -3. So that's my domain. But that also identifies my asymptote. My asymptote then happens at x equals -3. So on a logarithmic function, the barrier for the domain is the asymptote. So at -3, there's an asymptote. The graph gets close to it. We'll have that kind of shape. Don't forget, these things don't turn over. And so I can see that that my graph is going down to -infinity, close to the asymptote, and then out to the right, it's slowly growing and growing and growing. This does not flatten out. None of these have asymptotes both vertically and horizontally. So logs do keep growing, just very, very slowly. So the range here is -infinity to infinity, and the domain is bounded by the vertical asymptote. Finally, this is the first stuff we did in this unit, so I don't want you to forget about that. This is section 3.4. And it's just drawing piecewise defined functions. Again, the most important thing here was to identify the transition point. So this graph, I just draw a little dashed line there. That's not an asymptote. I'm just trying to remind myself that's when it happens. So at x equals 3, you can see that there's a transition between these two pieces. And if I keep that straight, then all I have to do is draw this picture to the left of that line and this picture to the right of that line, and everything should be fine. So I'm going to do that by plotting points, since these are straight lines. I'm going to plot f of -4 and f of 3. Both of those values are included in this inequality, so those would use this definition. So 2 times -4 minus 3 is -11. That's not a great point. Oh, it is on my graph. Okay. 6 minus 3 is 3. So at -4, -11, somewhere in there. And at 3, 3, so 3, 3 is about here. I'll have like that. I draw sort of exaggerated dots on the ends because those are included. -4 is included in here, and 3 is included in here. So that's what the left side looks like. The right side, I would get by plotting a couple of points to the right of that thing. So I might say f of 4. That's not good. Let's say f of 6. I see the third in here, so I'm afraid of doing f of 4. So f of 6 is 2 minus the third of 6, which is 0. And then I could actually plot f of 3 using this thing, using this piece, because this is the transition point, and this point may not be on the curve, but it will tell me where my open circle goes otherwise. So notice that f of 3 is 1. So the right-hand graph will have an open circle at 3, 1. It's open because 3 is not actually included here, but it's an open dot there, and so the line is going to go down like that and continue on because this part of the domain keeps going. So this graph does have a discontinuity at the transition point. There's a jump there, but that's what the graph looks like. The intercepts you can find by just finding the x-intercept of this piece and the y-intercept of this piece. And then on this piece, only the x-intercept matters. This piece doesn't go over here, so only this piece's x-intercept will matter. So that's where you get the 3 intercepts. It's the x and y-intercept of this piece and the x-intercept of this piece. Without drawing it, it's hard to know which piece is going to give you which intercepts, and so a quick sketch of it to get a sense for how it's crossing is important before you try to find the intercepts.